As we already talked about the radial flow turbine in the reaction turbine sections, now we proceed to the other type of reaction turbine, that is the axial flow turbines. And one of the most widely used axial flow turbine is called as Kaplan turbine. So the turbine itself named after an Austrian engineer named Victor Kaplan due to his work back in the early 20th century, and his name is being used to name of one of the most widely used axial flow turbine. So looking at the constructions of a commonly found Kaplan turbine, we can divide them into 5 sections. So let's say this is 1, 2, region 3, 4, and 5. So 1 is normally the fixed guide vane. Second is the adjustable guide vanes. So it can be more than one guide vanes. It can be more than one fixed guide vanes. It can be more than one adjustable guide vanes. The third part is the transition passage. The fourth one is the runner or the blade itself. So the blade itself looks like a propeller here. And the last part is the draft tube. So when a constructions of an axial flow turbine doesn't have any adjustable guide vanes, let's assume that it only has a fixed guide vanes, the turbine can be called a propeller turbine. But when it equipped with these 2 guide vanes, it can be called Kaplan turbine. One thing that we need to notice that this type of turbine or type of axial flow turbine is being used for conditions where we have low head and high flow rate. So, and the other thing that we need to remember also that in the common applications of the Kaplan turbine or any axial flow turbines, the number of blades in the runner, so blades is here, is normally between 4 and up to 6 blades in one runner. And when analyzing the velocity triangle, normally the velocity triangle is being analyzed at the mean radius of the runner. So let's say that we have the blade of the runner that looks like this from side view. So the mean radius is the average between the tip and the hub of the runner's blade. So we call this as runner, and the blade is one single twisted profile that attached to the center here. So all of this analysis for the velocity triangle are being done at the mean radius value. So now let's have a look at the velocity triangle itself. As we know that the flow between the inlet and outlet in any axial flow machineries are identical, therefore the first assumption that we need to make is that the radial component, CR1 is equal to CR2 and it's equal to CA. And by looking at the velocity triangle, we divide them into the inlet and outlet area of the blade or of the runner, and we can see that the blade velocity, or U, is Riemann constant for U1 and U2 is equal to U. And at the inlet we have the blade angle, an absolute angle between C1 and U1, and the blade angle is between the relative velocity and the blade speed of U1. And to get the Euler equations, or the Euler turbine equation for the axial flow turbine, we know that E is equal to W divided by M multiplied with gravity, or we can write it down as U multiplied with Cx1 minus Cx2 at the outlet divided by gravity. And for conditions where we have zero whirl at the outlet, means that Cx2 is equal to 0, the Euler equations becomes U multiplied with Cx1 divided by gravity. Now let's have a look at the positions of Cx1 here. So Cx1 is a function of U1 minus Wx1, or we can further elaborate that U1 is minus to the Ca, or CR1 in this case, multiply with the cotangent of 180 minus beta 1, and this is how we define Wx1, or to put it in a more simple way, it can be U1 plus Ca multiply with cotangent of beta 1, or blade angle at the inlet, and this is Cx1. Now we put this Cx1 back to these equations. The final form of the Euler equations becomes U to the power of 2 plus U multiply with Ca multiply with cotangent of blade angle at the inlet, put a bracket here, divided by gravity. So this is the Euler equations for an axial flow turbine, or in this term is the Kaplan turbine.